Good morning, students. Let me start the class now. In the last class, we solved one exercise on self-bias. Today, let us see one more exercise. In the last class, I told that the previous exercise, that into symbol is wrong, maybe it should be plus. Actually, that into symbol is correct. I verified later on. Whatever way I had worked out the exercise, that is accurate. Out of some confusion during explanation, I told I will verify that later on. But later I have verified it is correct. So today let us see the next exercise. Given IB equals 15 microampere, find RB for the Q point to be at the middle of the load line. This is the exercise given. So if the Q point has to be at the middle of the load line, here VCC given is 18 volts. So here it must be 9 volts. And how to find out the current? IC sat we can find out assuming saturation here 18 volts divided by 2.2K plus 1.1K is 3.3K. Always visualize if the transistor is completely switched on, then the current is going through this 2.2 kilo ohms and 1.1 kilo ohms through RC and RE. So the total resistance from VCC to ground is 3.3 kilo ohms. So naturally, IC sat is 18 volts divided by 3.3 kilo ohms. So that way, the value of Q point is indirectly given in this exercise. Okay. And he is asking to find out RB given IB is 15 microamperes. Now let us see how to solve this. We already know the Q point, right? So IC sat is 18 volts divided by 3.3K. 2.2K plus 1.1K is 3.3K. So IC sat is 5.45 milliampere. So naturally ICQ will be 5.45 milliampere divided by 2. Therefore the Q point is 9 volts. Q point ideally must be VCC by 2. So 18 volts divided by 2 is 9 volts. 5.45 milliampere divided by 2 is 2.73 milliampere. So Q point is found out. IC is found out now. Okay. Now, if this IC is found out 2.73 milliampere, then naturally VE is RE into IE. So that is 1.1 kilo into 2.73 milli. That K and M, anyhow I am cancelling it out. So we get VE equals 3 volts. When we get VE equals 3 volts, VB is nothing but 0.7 plus 3 volts because it is VBE plus VE. So VB is 0.7 plus 3 volts, that is 3.7 volts. Now you know this VB, you know this 18 volts. So the voltage across this RB is 18 minus 3.7. And he has already given the current 15 microampere. That particular voltage divided by 15 microampere is going to the value of RB. So RB is 18 minus 3.7 divided by 15 microamperes is 953 kilo ohms. This is one method. It's a straightforward method. Find out IC sat, find out Q point, find out VE, find out VB, find out RB. This is one method. The same problem can be solved through another method. That another method is by finding out the beta itself. Now when you know IC, when you know IB, you can find out beta. So by finding out beta, you can substitute that value of beta in the value of IB. Because you know the formula for this particular circuitry, IB is VCC minus VBE divided by RB plus 1 plus beta into RE. All other things we know, we don't know beta, we don't know RB. Now if we find out beta, we can easily find out RB using the equation of IB. That is another method. Always in nature, for any one particular problem, there are multiple solutions. Same way, even in engineering or in technology or in science, for one particular problem, there can be multiple solutions. Even in life, for one particular problem, there can be multiple solutions. It is not right to think that one problem can be solved only through one method. Because there can be multiple solutions available for a given problem. For example, you are hungry, you want to have a breakfast. Now you are hungry is the problem, for which what you want to eat or what you want to have, you have multiple choices. If you go to a restaurant, you will have multiple choices to consume what you want to have for today's breakfast. You may not have the choice if your mom has already prepared a particular breakfast. But again, tomorrow you can ask your mom to prepare a different breakfast, day after tomorrow different breakfast. Hunger remains the same, whereas the food is having multiple choices. So that way, for any problem, there can be multiple solutions. Same way, this problem, this is one way of solving. We will solve it in another way by finding out the beta. Now, beta we can find out 2.73 milliampere divided by 15 microampere. We have already found out the Q point. So, IC by IB is beta. We get beta as 182. When we get beta as 182, substituting this value in the equation for IB, I have directly substituted that value. 15 microampere into RB plus 183 into 1.1K equals 17.3. This I have substituted VCC minus VBE divided by RB plus 1 plus beta into RE. The denominator I have brought to the left hand side. So IB into RB plus, this is beta plus 1 into RE equals VCC minus VBE. When you solve this equation, or RB equals 17.3 minus 3.02 divided by 15 microampere. This 3.02 is nothing but this 183 into 1.1K. So, divided by 15 microampere, you will get the same value as 953 kilo ohms, or slightly lesser, maybe 952 kilo ohms. You will get minor differences there, but that can be ignored always, because when the value is around 900 kilo ohms, that 1 kilo ohm, 2 kilo ohm difference does not matter. So, this is how we can solve this problem. If you have any doubt in this problem, you can always ask me, or you can put the questions in the Google class also. I will keep checking the Google class as well, and there also I will answer your questions. Now, let me go to the next method. We have this voltage divider bias. And I had already discussed this voltage divider bias as accurate analysis and approximate analysis. This is just a revision now. I had told you that out of all the three biasing circuits, voltage divider bias is the most stable biasing circuitry. Later on, I am going to show you one more exercise where I am going to compare base bias with the emitter bias for the same Q point, and later on I am going to show you how the change in beta is going to affect both the circuitry. That anyhow we will discuss that in one of the next exercises. So this voltage divider bias, let us see the accurate analysis. Now we can replace this circuitry by means of this particular equivalent circuitry. Here VCC is connected to R1, then we have R2. So VCC is connected to R1, then there is R2 with respect to ground, then R1 and R2's junction is connected to the base, then we have this RE. So we can write a Thevenin's equivalent circuit. You are going to study a course called network analysis. There you are going to study more about Thevenin's theorem, Norton's theorem, and many other circuit related theorems. I will not go into too much detail about the Thevenin's theorem now. Thevenin is the name of a scientist who could find out how to write the equivalence of a resistive network. So here, if we look from the output side to the input side, we can see this R1 in parallel with R2 as far as AC signal is concerned. I had discussed about what is the meaning of the AC ground in one of the previous classes. When you have input here and that input AC is coming here, that AC is going all the way to VCC as well through R1, it is going to ground as well through R2, and it is going to the base of the transistor. Now R1's other end is VCC, other end of VCC is nothing but a large capacitor or a large battery which is going to absorb all the AC. So as far as AC is concerned, AC is becoming 0 at the top also, AC is become 0 at the bottom also. So we can say VCC is also AC ground and ground is also AC ground. However, the AC which is going to the base is going to initiate a switching action inside the transistor and we will get an amplified output at the collector. So, with respect to this, we can always take that R1 and R2 are in parallel. That itself is the Thevenin's equivalent now. So, we can write R Thevenin is R1 parallel with R2. This I had discussed with you earlier. I am just going to revise the same thing. So, here Boylston calls this equivalent resistance as RTH or R Thevenin, because Thevenin is nothing but the equivalent circuit. Now, Boylston calls this voltage at the base as ETH, whereas in the Malvina book, he simply calls it as VBB, the voltage at the base. We can have the same convention also, or here we can call it as E Thevenin. Equivalent Thevenin voltage is nothing but the voltage across R2. The voltage at the base itself is the voltage across R2, that is nothing but E Thevenin, that is nothing but R2 into VCC divided by R1 plus R2. This also I had discussed earlier. It's a straightforward derivation that voltage across R2 is nothing but current across R2 into the voltage across R2 is nothing but the current across R2 into R2. So, the current across R2 is VCC divided by R1 plus R2, ignoring IB, and into that R2 itself is the VR2. Here we have a notation called ETH. So, using this, we can write the expression for the base current as ETH minus VBE divided by RTH plus beta plus 1 into RE. This is same as the self-bias circuitry, except that here we had VCC minus VBE and here we had RB. In case of emitter bias, the formula was VCC minus VBE divided by RB plus 1 plus beta into RE. Whereas here it is equivalent circuitry wise, the effective resistance is R1 parallel with R2 and the effective voltage at the base is nothing but VBB or VR2. So we are using this notation of ETH minus VBE divided by RTH plus beta plus 1 into RE. So, whatever formula you are remembering for the emitter bias, remember the same formula for the base current for the voltage divider bias. The only difference is at the numerator, instead of VCC, it is ETH, and at the denominator, instead of RB, it is RTH. And you always remember that RTH is nothing but R1 parallel with R2 and ETH is nothing but the voltage across R2. This way, if you remember, you can easily solve the exercises meant for this biasing circuitry. Now, this is the accurate analysis, and we had already seen what is meant by approximate analysis. Let us see that now again as a revision. Now, approximate analysis, we have VCC, we have R1 and R2, we have this IB, we can always ignore IB. Provided I2 and I1 are almost equal, we can always ignore IB. Now, when you look into the base, you will see a input impedance. I'll just come back to the previous slide. When you look into the base, you will always see an input impedance here or input resistance here, because it is nothing but base to emitter junction there. So, base to emitter junction will have its own finite resistance, and even this RE will get added to that resistance. And we have an amplification factor of the current inside the transistor, which means that when the AC signal comes inside, it is going to see an impedance here. The impedance in the term of AC and resistance in terms of DC as such. And we can identify or indicate it as Ri itself, resistance itself, because anyhow resistance is going to affect both AC as well as DC. you already know that capacitor blocks DC, passes AC. Inductance blocks AC, passes DC. Whereas resistance blocks both AC and DC. When there are all these three in a circuitry, then we call it as impedance. Impedance is the effective resistance along with effective reactance. So for capacitor and inductor, when they also resist the flow of current, we don't call it as resistance, we call it as reactance. The net effect of resistance and reactance is nothing but impedance. So the AC signal is going to see one impedance or resistance. For this particular analysis, let us ignore the capacitive effects. We will assume that all the capacitors are passing AC at this point of time. Later on in the module 3, we are going to go into more detail about the capacitive effects of the transistor also. So for the particular module, let us suffice it to say that we are ignoring all the parasitic capacitive effects that are occurring inside the transistor. Then we can say that there is an input resistance of Ri, and in general this Ri is much larger than R2. This anyhow we are going to find out later on when we perform AC analysis for the circuits. Right now we are only performing DC analysis. After we complete this DC analysis, we are going to discuss the AC analysis of the same circuits: base bias, emitter bias and voltage divider bias. So in general, the impedance is much larger, and you already know, you may be recalling whatever is discussed in the first year, or else again I am going to repeat that any given amplifier must have a very large input impedance, it must have a very less output impedance. We are going to discuss these things again in AC analysis. So until then you don't worry, but you just remember that any amplifier ideally should have a infinite input impedance and it should have a zero output impedance. So this Ri will be naturally much larger. When Ri is much larger, then we can simply ignore IB. Let us say this R2 is around 3 kilo ohms and Ri is around 100 kilo ohms. If Ri is around 100 kilo ohms and R2 is around 3 kilo ohms, naturally the current going into this Ri is much lesser. So that way we can approximate I1 equals I2 and we can ignore IB. That is the essence of approximate analysis. Okay. Now let me go further. This is our assumption that we can ignore IB. That is what is approximate analysis. Whereas in the previous approach, we did not ignore IB. You can see here, we did not ignore IB. When we calculate IB, considering beta, we can calculate IC. When we calculate IC, we can calculate VCE. Bhargav Dayal is saying screen is not visible. What about others? I have shared the screen. What about others? Students respond. Is it visible or not? Yeah, it is visible.
Well, sir.
Yeah, Bhargav, you please refresh once again. Okay, fine. Let me proceed. So, in the accurate analysis, we are actually calculating IB. After that, we can calculate IC, we can calculate VCE, we can arrive at the Qpoint. That is accurate. Whereas in approximate analysis, we are going to ignore IB. When we ignore IB, our life becomes simpler here. But later on, I am going to tell you, it is not going to be so easy. There are some conditions that I will discuss later on. So, here Ri is beta plus 1 into Re, because at the other side you have IE, at the input side you have IB. So, the signal which is coming at the input is going to see an impedance of beta plus 1 times more along with Re, because IE is beta plus 1 into IB. So we can safely say that the input impedance of this transistor at the base is beta plus 1 into RE. In general, beta is always 60 or 80 or 100, sometimes it is 200, that way it is more. And when it is multiplied by RE, the value of RI is going to be much larger than R2. That way we can ignore this IB. Now when we ignore the IB, I2 can be considered as equal to I1 only when Ri is much larger than R2. Now this is the specific condition. Only if Ri is much larger than I2 R2, then only IB can be ignored. Otherwise IB cannot be ignored. So we have to make a careful choice of this value of R2. Only then the approximate analysis is going to help us. So hence, ignoring this 1 in this expression, we can have a thumb rule that beta into Re must be greater than or equal to at least 10 times R2. See, we have this thumb rule, we can ignore this 1. So Ri is beta into Re. So we can always say that it must be greater than or equal to at least 10 times that of R2. Only then this approximate analysis is applicable. Otherwise, let us say the R2 is also larger, then IB may not be ignored. That is the point here. So remember this, if at all we have to perform an approximate analysis for any voltage divided by a circuit, then this condition must be satisfied. Beta into Re must be greater than or equal to 10 R2. This condition is satisfied, then only the approximate analysis is holding good. Otherwise, the circuit again depends on beta. From the beginning, I have been telling that we want to have a circuitry where we can ignore beta, we can ignore IB, we can ignore the effects of temperature, and we can ignore the changes in VBE. All those things I have been telling you. Only in such a case, our circuit will be very stable. It will work in any temperature. It will work with any transistor. That was our requirement. But now, only if this condition is fulfilled, then our voltage divider by a circuit is a very good circuit. It is a very stable circuit. If this condition is not satisfied, then the voltage divider by a circuit also will have variations. That we will see in the next exercise. Okay. So this condition will ensure that the approximate analysis is accurate. Now based on this particular assumption, let us solve one exercise. Just a minute, I have an exercise here. Just a minute. Okay, I have now two exercises. This particular exercise I will tell you now. Later on, let me go on to that approximate as well as accurate analysis exercise. So, there is one exercise here. You can see, given VCC equals 12 volts, beta equals 50, design fixed and self-bias circuits for Qpoint given this way and compute the Qpoint for the same circuit when beta equals 80. This WebEx's top point is blocking me to see the upper line. Okay, anyway, now it has gone. Given VCC equals 12 volts, beta equals 50, design fixed and self-bias circuits for Qpoint 6 volts and 2 milliampere. VCC 12 volts, so ideally Qpoint must be 6 volts. And it is given ICQ is 2 milliampere. Compute the Qpoint for the same circuit when beta equals 80. So, let me solve this exercise. I have already solved it. Let me show you the results. Let us first design a fixed bias. For a fixed bias, now RC is 12 minus 6 divided by 2 milli. You will have to simply visualize the circuitry now. Always in electronics, we will have to visualize the circuitry in front of our eyes. I have been telling you that electronics branch is not as easy as the other branches, because in all other branches, whatever they work on is visible. For example, for mechanical and automobile engineers, whatever they work on is visible. Even for civil engineers, whatever they work on is visible. Even for electrical engineers, whatever they work on is visible. At least for computer science and information science engineers, whatever they work on, at least the code or the program, that is visible. Whereas in electronics and communication, neither the electron is visible nor the radio wave is visible. Still, we have to discuss electronics and communication. Communication is basically radio communication, wired communication and wireless communication. But radio wave is not visible. You will have to visualize the network, you have to visualize the radio wave. Same way, electron is not visible, still you have to visualize the electron moving into the transistor's base. So now, you will have to visualize the fixed bias circuit in front of your eyes. That there is RB, there is RC, there is a transistor, NPN. You visualize that way. So when you visualize that way, VCC minus VCE, because he has given the Qpoint is 6 volts, VCC minus VCE divided by he has given the IC 2 milliamperes. So VCEQ and ICQ are given, VCC is given. So RC is 3 kilo ohms for a fixed bias circuitry. Now IB can be found out because ICQ is given 2 milliampere divided by beta is given 50. So IB is 40 microamperes. When IB is 40 microamperes, RB can be found out. RB is VCC minus VBE divided by IB. 12 minus 0.7 divided by 40 microamperes is 283 kilo ohms. When beta equals 80, what happens? Let us see. We will replace the same thing. Now RC value we know, RB value we know. Now we will simply replace that beta equals 50 with beta equals 80. So we can find out IC is 40 microampere into 80 because IB remains the same. IB remains the same because there is only one RB there. So IC is 40 microamperes into 80 is 3.2 milliamperes and VCE is 12 minus 3.2 milli into 3K is 2.4 volts. Now look at this. When beta was 50, Qpoint was 6 volts and 2 milliampere. When beta became 80 with the same resistor values, the Qpoint became 2.4 volts and 3.2 milliampere. Just look at the drastic difference here. 6 volts became 2.4 volts and 2 milliampere became 3.2 milliampere when beta changed. That is the problem with the base bias circuit. That is why we are not using it anywhere. We are using it only in digital circuits for inversion. Otherwise, we are not using it anywhere for amplification in the analog circuitry. Now, I hope you understood this problem. We designed a fixed bias circuit for the given Q point, then we replace the beta with a different value and we are finding a drastic change in the Q point. So fixed bias is not a good circuit because the bias remains fixed there. Now, let me work out the self-bias circuit. In case of self-bias, you have to again visualize one RB, one RC and one RE. Now here the design is not really very easy. Only knowing the Q point is not sufficient for designing the self-bias. We have to make an assumption here. The assumption is let VE equals VCC by 10. This assumption we have to make when we have to design a circuit or when we have to choose the resistor values. The reason is now only IC is known, that means IE is known, but there are two unknowns, RC and RE at the output side, RB at the input side. Anyway, at the output side there are two unknowns. In case of the fixed bias, only RC was unknown. We knew the other two. We knew the voltage, we knew the current. We could find out this RC. But in case of self-bias circuitry, there are two unknowns, RC and RE. Now we have to make an assumption about this RE so that we can find out RC later on. Anyhow, this particular discussion is going to be discussed in detail in your lab classes when the lab teachers discuss the RC coupled amplifier circuitry. So in the theory, we are not going to go into deeper details of the design issues because anyhow it is there in the lab syllabus. But for this particular exercise, I will tell you that there is an assumption that let VE be VCC by 10. This is going to give us a safe area about the Q point. So if V equals VCC by 10, then we can easily find out RE as VE by IE. 1.2 volts by 2 milliampere, that is 600 ohms. Once we find out RE, we can easily find out RC. RC is VCC minus VCE, we already know 6 volts, and VE we already know 1.2 volts. So there is a voltage drop across transistor, voltage drop across RE. You will have to simply visualize these things now. You have no other option, I have no other option. We have to keep on visualizing the circuitry now. So 12 minus 6 minus 1.2 is 12 minus 7.2 divided by IE is 2 milliampere. We get the value 2.4 kilo ohms. So we got RE, we got RC. Now we can find out IB. IB is nothing but IC divided by beta, 2 milliampere divided by 50 is 40 microampere. Now based on this, we can easily find out RB. RB is 12 minus VB minus VE. Again visualize the self-bias circuitry. VCC is there at the top, then there is a base to emitter junction, then there is a RE, across RE there is VE. So 12 minus VBE minus VE, that is 12 minus 0.7 minus 1.2 is 12 minus 1.9. That divided by IB 40 microampere, we get the value 253 kilo ohms. Now this 253 kilo ohms, because students keep on leaving the meeting, they keep on waiting in the lobby, there must be that network issue. I'll have to keep admitting the students in. Anyway, let me continue. We found out this RB now. We have all the three values now. We have RB, RC and RE. Now, let us go for that exercise of when beta equals 80, what happens? When beta equals 80, I will simply substitute the equation of IB there, VCC minus VB divided by RB plus 1 plus beta into RE. So, as beta is 80 and actually IB is going to change. In the earlier case, IB is not going to change because the RB is fixed there. But in the self-bias, there is RE in the expression of IB. That is why we have to find out the IB once again, that is 12 minus 0.7 divided by RB plus 1 plus beta into RE, we get 37.47 microamperes. So, when IB changes, IC changes to IB into beta, that is 37.47 microampere into 80 is 3 milliampere, and VCE is VCC minus IC into RC plus RE, that RC plus RE is now 3 kilo ohms. RE is 600 ohms, RC is 2.4 kilo ohms, so totally 2400 plus 600 is 3000. That I have written it as 3K. So 12 minus 3 milli into 3K, we get 3 volts. Now look at this exercise, dear students. In case of fixed bias and in self bias, when beta was 50, Q point was same. Now when beta got changed, in fixed bias, Q point became 2.4 volts and 3.2 milliamps. Whereas in self bias, it became 3 volts and 3 milliamps. What does it mean? It means that when there is a variation in beta, it does not much affect with the self bias, it affects more with the fixed bias. But it is affecting both of them. Even self bias is not away from the problems. Even in self bias, we have these issues. That is why we have gone to voltage divider bias. But you can see here, in fixed bias, the VCE changes to 2.4 volts from 6 volts. Whereas here from 6 volts, it is coming to 3 volts. Again, in fixed bias, the current is 3.2 milliampere, whereas in self bias, it is 3 milliampere. That means, we can say that self bias is more stable than fixed bias is. But the self bias is also not fully unstable. That is the reason we go for voltage divider bias. So anyhow, I am going to share this PPT with you. If you do not understand these calculations, again go through these calculations in detail. And if you have any doubts, you can always come back to me for clarifications. Now let me go further. We have discussed this accurate analysis. We have discussed this voltage divider bias, approximate analysis. Now let us have an exercise for this VDB circuitry. Find Q point using both accurate as well as approximate analysis for the given circuitry here. Now I will not discuss again in detail about all those procedures. We have already gone through it. Let me go quickly about how to solve this particular problem. We can find out the R Thevenin. R Thevenin is nothing but R1 parallel with R2, that is 62K parallel with 9.1K, that is 7.94 kilo ohms. We can easily find out ETH or VBB. ETH is nothing but R2 into VCC divided by R1 plus R2. Here R2 is 9.1K, VCC is 16 divided by R1 plus R2, 9.1K plus 62K, that is 2.05 volts. Now when you found out this VBB or ETH, both are one and the same. Or you found out R1 parallel with R2 is nothing but RTH, both are one and the same. We can simply substitute these values in the equation for base current. So IB is ETH minus VBE divided by RTH plus 1 plus beta into RE. That is the equation for IB. Now substituting this, I get the value of IB as 21.42 microamperes. When I get this value, we can easily find out ICQ equals beta into IB, that is 1.71 milliamperes. Then we get VCEQ is VCC minus IC into RC plus RE. There is a drop across RC, there is a drop across RE, and we know that current is the same because always IC can be equated to IE. So that way we have VCC minus the drop across RC and RE, that is 1.71 into 4.58 is nothing but 3.9 plus 0.68 is 4.58 kilo ohms. That milli and kilo get cancelled and we get Q point is 8.17 volts. Okay, this is as far as the accurate analysis is concerned. We have the Q point as 1.71 milliampere current and 8.17 volts as voltage. Now let me solve this using approximate analysis. Approximate analysis is really very easy. How? Simply find out VE. Now let us see whether the condition is matching. Beta into RE must be at least greater than or equal to 10 R2. Is it matching? Let us see. Beta into RE. Beta is 80. RE is 0.68 kilo ohms or 680 ohms. So beta into RE is coming around 54,400. whereas 10R2 is coming to 91 kilo ohms. 10 into R2, 9.1 into 10 is 91 kilo ohms. So the condition is not matching here. You can see beta into Re must be greater than or equal to 10R2. It is not matching here. Here it is 54.4 kilo ohms. It is not actually kilo ohms. You can say kilo ohms only because there is Re here. It is 54.4 kilo ohms. Here it is 91 kilo ohms. Condition is not matching. So let us see in the approximate analysis what is the difference which we are going to get. So we can find out IE. IE is 2.05 minus 0.7 divided by 680. IE is nothing but we know this VB. VB is 2.05. We have this ETH. VB minus VBE is 0.7 divided by 680. That is 1.99 milliampere. You see the difference here? In the earlier case it was 1.71 milliampere. Here it is 1.99 milliampere. That means there is a difference. But if you compare this difference with the earlier circuitry of self-bias and fixed bias, there the differences are more. Here the difference is slightly less. Still the difference is there even in VDB. So the point is, if at all VDB has to be more stable, then we should always match this particular condition. Beta Re must be greater than or equal to 10R2. That is what we are going to use even in future in the labs. In the lab, when you are going to work out the circuitry of amplifiers and oscillators, always observe there that the condition is always met there. We design the circuit in that way only. Beta R will be always greater than or equal to 10R2. That is how we design the circuitry. Then only the VDB is stable. So let me continue. We got the difference here as IE. Let us find out VCE now. VCEQ is 16 minus 1.99 into 4.58. That 4.58 is nothing but RC plus RE. We get the value of 6.89 volts. You can see that in the accurate analysis it was 8.17 volts. In the approximate analysis it is 6.89 volts. That means there is a difference here. Now, dear students, I have already given you the PDF copy of the textbooks. There are so many exercises in the textbooks. All those exercises you also have to work out and practice. Only when you practice personally, then only you will understand these things. Otherwise, we teachers will keep on completing class after class, module after module. Within this month itself, we have to complete 2 modules now. So, I am still in the first module. I will have to complete the next module also before your first internal test. So, in your free time, all of you have to study the textbooks once again and work out all those exercises, not only for this subject, for all other subjects also. You have got 6 courses now. For all the 6 courses, don't waste your free time. Keep on working out these exercises. Otherwise, it will become overloaded after a few months. When suddenly a second internal test also comes, third internal test also comes, suddenly the final examination also comes, and if you prepare at that time, you will really become overloaded. You may not be able to understand these things when you are under tension or pressure. So don't waste your free time. Don't think that just online class is going on and we don't have to worry too much. Whenever we want, we can come to class. It is not like that. Whether it is online class or offline class, understanding is really important. So if you have to understand, you will have to work out more and more of these exercises. So please go through the textbook, go through all those exercises. I can solve only some of the exercises in the textbook and I can create some of my own exercises. I created that particular exercise of fixed band and self-bias on my own. But I cannot solve all the exercises which are there in the textbook. You only have to work it out in the free time. So, you work out one exercise which is there in the textbook where beta Re is greater than or equal to 10R2. That condition is met there. When the condition is met there, the difference will be much lesser. I have not shown you here because anyhow it is going to be meeting the conditions. So there is no point in solving that exercise. I chose an exercise where the condition is not meeting and I wanted to show you the difference there. So if we want to have a stable voltage divided by a circuitry, then we should have this condition being met. We should design the circuit in that way only. That is where we have to choose the RE. So that is where I told you we should choose VE equals VCC by 10. Then we have to choose an RE based on the value of RE. We have to choose the value of R2. Later on we can choose R1 and RC. All those design details anyhow in the lab teacher is going to discuss with you when you practically work on these exercises. Okay, it is time now. Come back to Google class. In the Google class, I am going to post the quiz.